The first thing I want us to write down here for the formula shortcut is that we do not write the subscript of 1. So put a note for yourself. Do not write subscript 1. So we proved kind of where the electrons are going, where they're coming from in each of these examples up here. And remember that when we wrote our formulas, if we only used one of an atom, just listing it counts. We don't need to put a subscript of 1. So anytime it's a 1, it's just kind of implied. And then to use the crisscross bonding shortcut, you're first going to find the charge. Another word for charge, do you remember what we've been calling it? Not stable. Okay, you guys are saying good words. Things will get a charge because they want to become stable. If you have a charge, you're called an ion. What I was trying to get at was oxidation number. So I use those words interchangeably. If I say oxidation number, that means charge. If I say charge, that means oxidation number. So you're going to find the charge, which is different than how we started each of these. Remember here we were looking for valence electrons when we're actually going to draw it. But here, for the shortcut, we use the actual charge, the oxidation number. And the key is that you are going to crisscross just the number without the actual charge sign, without the positive or negative, so that it becomes the number of atoms needed to bond and fill up all valence shells. When you're done, you'll double check that the formula is in the lowest ratio and it cannot be reduced. And the overall charge on the compound should equal 0. So let's start by doing some examples. These two are the ones that we just drew, but I wanted to show you that it will match up if you do the shortcut versus the long version of drawing it out with the electrons and arrows and all of that. So if I have calcium and fluorine, my first step is to find the charge of each of them, the oxidation number. So for calcium is right here. Its oxidation number is +2. Calcium is still my cation. It will still come first. And fluorine is my anion that will come second. So fluorine is right here. What is fluorine's oxidation number? So notice there are 2 numbers written above it. Previously, when we did this, we used the 7 because that's the number of valence electrons, but that's not what we're using in this case. We're using the charge, so -1. So with those listed, the positive and negative tell you which one's going to come first, and so calcium comes first in my formula, Ca. This 1 for fluorine tells me that I need 1 calcium. And so just writing Ca tells me I have 1 calcium. This 2 over calcium tells me that I need 2 fluorines. So I would write F2. And then notice that after doing this shortcut that took a lot less time, we came up with the same formula as when we actually went through and drew it with the valence electrons and showed where everybody was going and proved that they were all stable. We still came up with the same formula of CaF2. So the shortcut is a lot faster and a lot more convenient in most cases. But the drawings kind of give the background. And then same thing with Na and N. Sodium is Na. So right here, what is sodium's oxidation number? +1. So the positive tells you that it would come first. And then nitrogen's oxidation number, -3. So notice on this side, it really matters which number you use. On the cations, it doesn't make a difference since they're the same number. But here, if you used a 5 versus a 3, it would give you a different number. Or different subscript, of course, different number. So the 1 tells us that I need how many nitrogen atoms? Just 1. And the 3 tells us I need how many sodium atoms? Perfect. So when I write it, I still write sodium first since sodium was my cation, Na. And then a subscript of 3. And then N. So again, that came up with the exact same formula that we had when we drew the example for sodium and nitrogen. I'm going to pause this and give you guys a second to try these last three on your own, and then I'll restart when we go over our answers.